Hello, everyone. I'm Wes Brewer. I'm currently with the Department of Defense's High Performance Computing Modernization Program, working in the User Productivity Enhancement and Training Group, also known as PET. I'd like to share with you our work on scalable interactive autonomous navigation simulations on HPC. This work could not have been performed without my collaborators, including Joel Brettheim, also from the PET program, John Kanyars of DevCom Ground Vehicle Systems Center, and Palin Song and Berman Gates of the Engineer Research and Development Center. Autonomous navigation has received much attention these days due to the impending possibility of full self-driving cars being deployed into production. For example, in responding to criticisms why Tesla has not deployed full self-driving ability into production, Elon Musk recently tweeted, "They have no idea how hard full self-driving is. The only path to success, in my opinion, is hardcore real-world AI software with dedicated neural network inference acceleration, ASICs, in-car, multi-billion-dollar neural network training supercluster, and 10+ billion miles of vehicle data. Good luck." Musk succinctly lays out many of the challenges involved: generating significant amounts of data, training neural networks on supercomputers, and inferencing on specialized AI accelerator devices. Moreover, at the GTC conference in March of this year, Jensen Huang announced NVIDIA Drive Map, which will provide a simulated environment of 500,000 kilometers of roadways in North America, which can be used to train and validate neural networks. We also often see quotes from NVIDIA such as, "Eventually everything that moves will be autonomous," suggesting how strong a focus they have towards the development of autonomous mobility. Finally, Amazon Web Services recently released Autonomous Mobility, a cloud-based solution for aggregating navigation in support of autonomous vehicle development. Our work addresses a number of these issues, but instead of using real vehicle data as Tesla does, we use data derived from a simulated environment to train the neural networks. Instead of using simulations of mapped roadways as NVIDIA envisions, we are supporting both on-road and off-road mobility. And instead of deploying in the cloud as AWS is doing, we are deploying on supercomputers. One of the important applications of autonomous driving in the Army is something called manned-unmanned teaming, or MUM-T, where you have a human teaming with an AI. One example of this is the leader-follower program, where you have a lead manned vehicle which can lead a convoy of one or more follower unmanned vehicles accurately and safely, up to 8 vehicles. This Army program has inspired a similar commercial application from a startup called Locomation, where you have two 18-wheelers driving in tandem, where the lead truck is manned, but the AI drives the follower vehicle to allow the driver to sleep. They call this human-guided autonomy. The leader and follower can swap every 8 to 10 hours or so. They show 130% utilization increase and 45% less operating cost using this technology. While there has been prior work in autonomous navigation on HPC, our work is unique in being able to launch such leader-follower applications, which requires communication between a number of different software components using several different protocols. So why the need for HPC? In this quote from ANSYS, they say, "Autonomous vehicle technologies could not be developed and validated without high-performance computing simulation. The LiDAR, camera, and radar systems that enable autonomous vehicles require multiple redundant sensor systems that must be simulated for performance and safety." In this project, we are performing a software-in-the-loop simulation, which consists of the Virtual Autonomous Navigation Environmental Sensing Engine, or VANE ESE, which is primarily used for physically realistic simulation of LiDAR, along with the Autonomous Navigation Virtual Environment Laboratory, or ANVIL. VANE ESE envelops a number of components, including the environmental sensor engine that has a number of virtual sensors, such as LiDAR, GPS, and cameras, also lighting and weather. Scenes including vegetation, terrain, textures, and structures, and real-time mobility and modeling and simulation with different types of terrains, vehicle models, and dynamic obstacles. And these components communicate with each other using ROS, the robotic operating system. For vehicle simulation and graphics, we are using ANVIL, which has both a simulation component and a graphical user interface. The overall architecture of our solution is shown here. We provision multiple compute nodes on the HPC, with one which we designate as the head node, which is running multiple singularity containers. The first container is an ANVIL GUI container, which runs on the host network. Then we can run one or more containers running ANVIL Sim on a virtual network with RTK, the robotic technology kernel, and multiple instances of vein containers running across multiple nodes via MPI and OpenMP on the HPC, and running simulations of the environment, as well as feeding LiDAR data back to Anvil. We use iLauncher to launch the entire process, which uses XFCE, which is a lightweight desktop environment for Linux that provides a virtual desktop environment to interface the HPC. The XFCE container also runs a VNC server with a no VNC client, which allows us to display the XFCE desktop in our browser window on our laptops. So you can see we have a number of containers and services intercommunicating to provide real-time, scalable, interactive autonomy. In order to simulate the MUM-T leader follower example mentioned earlier, requires launching multiple instances of these containers. To fully test the network virtualization capability, we tested a deployment of 2 full Anvil RTK instances on an HPC compute node. In this figure, the top row of boxes is the lead vehicle, whereas the bottom set of boxes is the follower vehicle. The key technology to allow us to run multiple instances of Anvil simulation on a single compute node is Singularity's Container Network Interface, or CNI, which allows the creation of a virtual network so you can assign a unique IP to each container. There are a number of issues when using virtual networks, such as the virtual IP address breaking the license authentication for the Anvil GUI. Our solution to that was to run Anvil simulation in separate containers on a virtual network while running multiple instances of the Anvil GUI using different port numbers on the host IP. In order to simplify the entire launch process, we used iLauncher to launch the XFCE desktop on a compute node. iLauncher submits a PBS job to launch an XFCE desktop over VNC and establishes a double hop SSH tunnel through the login node to the compute node so that we can display the remote desktop on our laptop via web browser. When iLauncher is started, it will open a browser window to the localhost URL. From this window, the user may select the desired HPC, node type, queue, number of requested hours, the account number, and select what applications they want to launch. iLauncher will then pop up another tab with an XFCE desktop as shown here. Here we have Anvil running in the background screen here. You see a smaller, so it's here, and you see a smaller Xterm screen showing the different software components launching up. And we're running VeloView here to show the visualized LiDAR point cloud maps in real time for the leader follower simulation. And you can see these virtual desktops that XFCE provides up here. And the way we use these is to have different virtual desktops interface to different compute nodes. We can use one for running the interactive simulation, another for running vein simulations, et cetera. And if you have multiple monitors, you can have each monitor showing a different information by opening up a web browser to the URL on each monitor. So why do we need to scale up our vein ESE simulations using MPI with OpenMP? Dynamic environmental conditions such as rain, snow, or dust particles may substantially affect the real-time performance, denoted here by the black line. In this figure, we perform the same LiDAR simulation with clear, snow, and heavy rain conditions on a single compute node using 24 OpenMP threads. Here we observe a 2 to 3x slowdown due to snow and rain conditions that kick it out of real-time performance. For our scale-up studies, we tested 4 different HPCs called Gaffney, Narwhal, Onyx, and Vulcanite. There's a big difference, especially in the number of cores per node among HPCs, with Narwhal having the most at 128 of the AMD EPYC Rome CPU cores. We first benchmarked vein ESE with what is known as the demo scene, consisting of primitive shapes with rain. We have runtime on the y-axis here, where lower is better, and x-axis is the number of CPU cores. We compared 3 different HPCs here. We see Narwhal on the yellow line wins here because you can use all 128 processors on a single node, with Onyx coming in second. And for the Vulcanite nodes, we ended up testing multiple node types. So the 6126 processors have 12 processors per node, whereas the 6136 is a faster processor, which has 2 CPU sockets for a total of 24 processors per node. And because of these numbers, we had to scale across multiple nodes to get up to 96 cores. So you can see we scaled up to 4 nodes here for the 6136 and 8 nodes here for the 6126. And you can see that Vulcanite nodes fall off quite quickly when going multi-node. And this study was performed using OpenMPI. Next, we performed a more in-depth simulations using a more realistic Camp Lejeune scenario, or Camp Lejeune scene, comparing between Gaffney and Narwhal using just 48 of Narwhal's 128 processors in order to have a direct comparison with Gaffney. The y-axis is also runtime, but the x-axis are two tuples here that with varying combinations of MPI processes and OpenMP, which each multiply to 48. This shows a few interesting things. One, Gaffney seems to handle multiple MPI processes better than Narwhal, as you can see by the flat line here. And you should always use less MPI processes than OpenMP threads for optimal performance. This may be explained by a paraphrase from centers.hpc.mil that says 2 MPI processes per node is optimal because there are typically 2 CPU sockets per node and 2 groups of cores sharing cache per processor. So that's what we see here, sort of an optimal between 1 to 2 MPI processes per node. In conclusions, we showed that autonomous navigation simulations on HPC is necessary for development of self-driving vehicles. We showed that Singularity's container network interface was instrumental for scaling up multiple vehicles on a single compute node. We demonstrated using XFC Linux desktop with no VNC and VNC with automated launching via iLauncher for interactive computing on HPC. We scaled up the LiDAR simulations using MPI with OpenMP, and we showed that that was necessary for maintaining real-time performance on HPC. We showed that using 1 to 2 MPI processes per compute node was optimal, and we are currently working on replacing Anvil with Unreal Engine 4 and scaling up to demonstrate a convoy of up to 8 followers per node on HPC, which is going to end up requiring about 17 different Singularity containers communicating, intercommunicating. So that's going to be this is a very challenging problem. Thank you very much.